So let's go ahead in this video and we'll see how to generate a clock for our CPU. So we want to generate a clock which will allow us to pass data from one part of the CPU to the other. So let's say, for example, we have one register here onto a bus and it's connected into another register, and we wanted to pass the information from this register onto the bus and into this register here. Then what we would have to do is we'd have to ensure that the clock, the enable, would go high, and when the enable goes high it would pass the information from this register onto the bus. So that's the enable going high here. But now we would have to ensure that that enable remained high until this register here was set. When this register is set, it takes the information from the bus and puts it into the memory location, and then whenever this set goes low, that information is now held within this memory location. At that point then the enable is able to go low. So you can see here that what we require is the enable pulse to completely enclose the set pulse. Now one way of doing that is shown here, and what we do is we take a clock signal, which is here, and we take a delayed clock signal, so this is delayed by 1/4 of a pulse, and then we can pass this clock and clock delayed through this little circuit here. So if you pass it through an OR gate, then you'll get an output when either clock or clock delayed is high. So in this instance here we're going to get this term here, so you can see that this one's high and this one's high, and they're high all the way along till we get to this point here, at which point both of them go low, and you'll get this little clock pulse here. Similarly, if you put both of them through an AND gate, you're going to get this clock pulse here. So that means that we've got two clock signals which do exactly what we require. The clock enable will completely encompass the clock set. Now it's not possible to build this type of clock in Logisim because we don't have this delay function, so we can't delay this clock in this manner. So we have to go and find a different method of providing a clock. So let's go and we'll look and see how we solve this problem. So let's go and we'll see how the clock has been implemented. Open up Logisim and head down to CPU_CLK, and this is the clock circuit here, just a small circuit. Now what we have at the heart of it is a JK flip-flop. Now JK flip-flops are available within the memory section, so it's a JK flip-flop there. Now we could go and build a JK flip-flop using purely a NAND implementation, and I'll show you how to build that just in a minute. But what we're going to do is we'll take this JK flip-flop and we'll tie both the J and the K's high. So what that ensures is that the output here, the Q bar, will toggle, but it will only toggle from a low to a high. So whenever I click that again, there won't be any toggle, and again it'll only toggle when it goes from a low to a high. So you can see here that this point here is running at half the clock rate of this point here, so it'll only change whenever that goes from a low to a high. So we take this here, and in effect this becomes our new clock. Our new clock runs at half the rate of this master clock. Now what we do to create the clock enable is we take the not Q out and we feed forward the value for the clock in to this NAND gate, and this will give us the enable. And the set was generated by taking the output Q and again feeding this signal forward into an AND gate and then inverting it. This will give us our clock set. So these are our three that we're interested in: our new clock, our clock set and our clock enable. Of course this circuit here will run a little bit slower because we've taken our original clock and we've halved the clock rate in order to generate this here, and it'll run even slower again because of the way the set and the enable have set up. So in effect, these clock set and enable will run at a quarter of the speed of this clock in, but that doesn't make much difference to us as long as it's fast enough just for us to see the simulations. So let's go ahead and we'll have a look at it and the timing diagram for this. So just before we look at the timing diagram, this here is the JK flip-flop, and it's done in a master-slave arrangement. Now we're not going to get into all the details of how this JK operates, but if you're interested you can always check it out online. All we need to know is that the operation whenever J and K are both set high, and that's as explained earlier. So let's move on, we'll look at the timing diagram. So this is the timing diagram here. We have our original master clock in. We have the new clock which runs at half the rate. And we have the clock enable here and the clock set. Now you can see from this point onwards that the clock set is completely encompassed by the enable. So you can see here that we could let the enable go high, and then there's another clock pulse till we get to this point here, and then the set would go high for a clock pulse, and then it would go low and there would be another clock pulse again, and this process would repeat over forever. So this is really what we're looking for. There's only one problem we have with this, is that we don't really want the clock to start at this point here. Okay, we really want the clock to start at this point here, because at this point here, this is where we ensure that the set is completely enclosed by the enable. Now we're able to do that, and we'll show you how we do that later on whenever we look at the control section, and we're able to adjust the stepper, which is a counter, so that it's only negative edge triggered, so it'll only trigger on this negative edge here. So one thing to note here is that it takes 4 clock pulses of the master clock in order to go through the one set and enable cycle. So for example, if we start from this point here, we're going to have 1 clock pulse, 2 clock pulses, 3 clock pulses, and then the 4th clock pulse, and then we start over again. We'll get 1, 2, 3 and 4 and so on. So it means that in effect this clock enable clock set, it's running at a quarter of the master clock, so it means that it slows the simulation up. But the good thing is as well is that it gives a lot of fine detail as to what's happening, because you can actually work through every single part of this clock set and enable whenever you're doing your simulations. But that's for a future video. We've got most of what we want here, so let's go and we'll actually see the simulation running in Logisim. So let's just look at the clock set and enable. What we want is the clock enable to go high, and then the clock set to go high, and then the clock set to go low, then the enable to go low. So watch this happening now. So we click on it and we've got the enable going high, then the set goes high, the set goes low, and then the enable goes low, and that process repeats over and over. So that's all we really want to do with the clock. But as I said, there's one small addition to this clock system to make the whole thing work, the CPU work, and we'll see that whenever we look at the section in the control unit called the stepper, which is actually a little counter. So let's have a look at this instance here. If we were in main and we come down to CPU underscore clock, then that's our clock instance, and you can see here you have an an input here, which is our master clock. You have the secondary clock, which is running at half the speed of this clock, and we have our enable and our clock set as well. So that's all there is for the clock. We'll get used to seeing how it works whenever we start putting together the whole CPU. So thank you for listening. I'll get you on the next video. Goodbye.